Hello everyone. Today we'll be covering a very small lesson, which is states of matter and ideal gases from CIE AL or AS chemistry. Uh, this lesson is fairly simple. It's comprised of introduction or basically a recap here because you've done IGCSE, I'm assuming, of the three states of matter: solids, liquids, and gases, and the different structures and their characteristics. And the new things in this lesson is the ideal gas equation and the kinetic model of assumptions, which these ideal gas equations are based off of, and simple volumetric conversions, and lastly, some additional points that are important that don't really fall into any of the categories that we'll be learning today. So I guess they're miscellaneous. Anyway, moving on with the lesson. So as you recall, there are three basic states of matter, and that is solids, liquids, and gases. Well, excluding the plural form, it's just solid, liquid, and gas. If you do AL physics, then there's also a fourth state of matter called plasma, which you'll learn about more in the nuclear physics of A2. But since you're in chemistry, that isn't really within the syllabus, so we won't be learning about that or covering anything about that. So regarding solids, as you know that they have fixed mass. Well, all of them have fixed mass. Same and same. And solids have a fixed shape and volume. Yeah. Liquids do not have a fixed shape, but the volume is fixed. Whereas for gases, they also have no fixed shape, but their volume is that of the container. They actually do have like fixed volumes as well. Like there's a certain volume of gas that's present within the container, but because the gases move about and have no forces of attraction between them, well, most of them, we just assume that it takes up the volume of the container. That's why we say it does not have a fixed volume. And regarding more about the particles of the objects in these states, in solids, the particle just vibrates or oscillates at fixed positions. In liquids, the particles move around each other. And in gases, the particles are, well, they don't necessarily interact, they mainly just collide with each other often. And the properties of these states are dependent on the molecule itself or the compound itself. For instance, I cannot generalize and say that solids have a high melting or boiling point because there's solid can like sodium chloride is a solid, but its melting point is really high. I believe it's above 1500 degrees Celsius, whereas iodine is also solid, but its melting point and boiling point is much lower, like in the 50s to 100 degrees Celsius. So the properties depend on the compound itself, so there isn't a general property when it comes to that. So that is just a brief overview of, or a brief recap of what you learned in your IGCSE years. They don't ask much about this, but it's best to keep it in mind. Okay. The next thing we'll move on to, what we just covered is a recap of solid, liquid, and gases and their structures and characteristics. The next thing we'll move on to is also another recap and something that you've come across in the previous lessons uh, when I talked about the chemical bonding between the different types of chemical bondings and the structures they form. So the different structures are in your syllabus are the giant metallic lattice, which is formed when like metallic bonds are formed. Giant metallic lattices, the properties are, you know what the metallic bond is, right? You know how the lattice looks like. Now we'll just talk about the characteristics. If you do not know or remember what the shape of the lattice is, I suggest you take a look at our previous videos. So the characteristics are layers can slide over each other. And these are the most important characteristics. This is something that you should keep in mind always, that they're malleable, ductile, and sonorous. And the last thing is that the electrons are delocalized. Therefore, the giant metallic lattice can conduct electricity. Yeah. Now these are the three characteristics that you have to keep in mind, where this is the most important one. So this is something that you must not forget. The next structure within your syllabus is alloys. Yeah. And what alloys are basically, if you remember from your IGCSE years, they're just a mixture of metals. Can be of different percentages. And the different cationic size, like the cations, because they're different metals, so the cationic size is different. Because the cationic size is different, the layers cannot slide over each other. As efficiently. And in most cases, alloys are stronger than pure metal. For example, the alloy stainless steel is stronger than iron. Yeah. Then we have simple molecular structures. And these are formed primarily by molecules that have covalent bonding between them. Their characteristics are they form they mainly form liquids or gases, but if they do form solids that have low MP and BP, melting points and boiling points, and the IMFs are easily broken when heated. So therefore, like this is the reason for this. Okay. The next type of structure is giant molecular. I don't remember, this is the fourth or fifth. I suppose it's the fourth. Giant molecular. And in giant molecular, they're mostly not conductors except for graphite, but they have high MP. Generally, not always. And that's pretty much it, I believe. And the layers can slide over each other in some cases. No, these are also not generalized, so they don't have specific trends. But generally, they have high melting points and boiling points. So some examples of giant molecular structures that you need to know about are graphite, diamond, and silicon dioxide. Sorry, not silicon dioxide, which is basically silica. Yeah, and You must know that this has high MP and BP. Layers can slide. Therefore, can be used as lubricants. And each carbon atom is bonded to 3 other carbon atoms, so they have like delocalized electrons and therefore are electrical conductors. Sorry, conductors, yeah. These also have high melting point plus boiling point. They're non-conductors. And since you have done molecule shapes now, you should know what the tetrahedral structure is, because each carbon atom is bonded to 4 others. It has an sp3 hybridization and therefore tetrahedral structure. And that's pretty much it. And silicon dioxide is similar to that of diamond. Yeah. And for those of you who do not know, silicon bonds like to 4 other atoms, and this is how it bonds to it. So there's one silicon, Si, 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 and Si, right? And in between each of these, there's an oxygen atom. That's what the structure of silicon dioxide looks like. If you want a more visual representation of this, I suggest you check out images in Google. Now there are 2 more types of carbon allotropes that are within our syllabus, and that is C60 fullerene and yeah, C60 Buckminster. I believe it's Buckminster. So Buckminster fullerene, and there was another one. Anyway, about this, so it has 60 carbon atoms. Yeah, and they have simple molecular structure. And therefore have relatively lower melting and boiling points. Okay. And one more thing about them is that they can, and I repeat can, conduct electricity. They can conduct it. It's not always that they will conduct, but they can conduct electricity. Anyway, the other one is something known as graphene. And these are much better conductors. Electricity, yeah, much better conductors of electricity. And in the past syllabus, not in the past syllabus, even in the current syllabus, but they don't ask it as much. But if you do practice A2 papers from before 2016, you'll see that the paper 4s have something called nanotubes. So whenever a nanotube comes, what you have to understand is that its size is very small, so approximately 0.5 nanometers. That is the size, or the diameter of the tubes, and that is basically what a nanotube is. That is formed, uh, with carbon. Now that is all about the carbon allotropes within your syllabus. I just briefly went over it because these are things that you learned in IGCSE. I didn't go much into depth. Anyway, the last part of this lesson is the ideal gases and the ideal gas equation. Now, before we go into ideal gas equation, what you have to know is the kinetic model of assumptions that the ideal gas equation is based off of. If you did A2 physics or if you did SAT physics, then you'll be very familiar with this lesson because it is from thermodynamics. In chemistry, we don't really go into the derivation of the ideal gas equation, so you just have to accept it at face value. And this is the formula: PV is equal to nRT, where P is equal to the pressure in pascals, V is equal to the volume in meter cube, not dm cube or centimeter cube. N is the moles. Sorry, the amount of substance. Well, that's a really long word, so I'll just write moles. R is the constant, ideal gas equation constant, and T is the thermodynamic temperature, which is in kelvins. Now, some basic conversions that you need to know is for T in degrees Celsius to T in Kelvin, you have to add to T in degrees Celsius, you have to add 273.15. Sorry, 273.15 to convert it to T in kelvins. In your syllabus, it's okay if you convert it, if you add only 273, but this is more accurate, so I prefer doing it with 273.15. So for instance, 25 degrees Celsius, how would you convert it to kelvins? The answer would be 25 plus 273.15, which would give you 298.15 kelvins. And it's the same way around. If you want to convert from kelvins to degrees Celsius, all you have to do is subtract it with 273.15. Yeah, and you'd get the thermodynamic temperature. Whenever they mention thermodynamic temperature, then you have to give the temperature in the unit of kelvins. That's an important conversion. Another important conversion is conversion like the volumetric conversion. So because you have to use meter cube in this one, you have to know how to convert from cm cube to meter cube and from dm cube to meter cube. So to convert from cm cube to meter cube, you remember that to convert from cm to m, you have to divide by 100. So if you want to convert 1 centimeter to meters, you have to divide by 100 and you'd get 0.01 meters, right? Now similarly, if you want to convert centimeter cube to meter cube, all you have to do is divide it by 100 cube. So let's say you want to divide 100 centimeter cube, the centimeters being cubed, right? So its convergence would be cubed as well. So it'd be divided by 100 cube, which is, I believe, really small value, 1 into 10 to the power minus 6 meter cube. Yeah. To convert dm cube to meter cube, all you have to do is divide by 1000. So let's say you have 1 dm cube. To convert it to meter cube, you have to divide by 1000, and you'd get 1 into 10 to the power minus 3 meter cube. For dm cube to meter cube, I prefer doing it like in steps rather than like this, which is first converting it to centimeter cube. So dm cube to centimeter cube is into 1000. So that would be 1 into 1000, which would be 1000 cm cube, and divide this by 100 cube. So 1000 divided by 100 cube, which would give you the same answer, 1 into 10 to the power minus 3 meter cube. The reason why I do this is because it helps me remember the conversion of dm cube to centimeter cube, which is very important in stoichiometric calculations. Now that this is also an important conversion that you need to know. Okay. Now let's get into the statements, or basically the kinetic theory, based on which the ideal gas equation is formed. This is the ideal gas equation, okay? And it basically is like the simplest way to remember it. Okay, how did this turn into a pentagon? I don't understand. Okay, it simply is like the best way to remember it, because you don't have to go much into an understanding of what it is. Wait, let me just erase this from the side so I'd have more space. The best way to remember it is by Ravid. I'll also explain on the side so that you understand like what each of the statements mean. So Ravid, the first part is R, which states random collisions. Sorry, random and rapid motion. Of molecules. Okay, random and rapid motion of molecules, which the first word is R, and that's why it's R. Sorry, the first letter is R, and that's why it's R. And what random and rapid motion of molecules means is that the motion is completely randomized. It does not have any trends. The second assumption is that A, so attractive forces between molecules are negligible, such as IMFs. So let's say normally an atom, such as diatomic molecule, such as bromine, to consider it as an ideal gas, we have to ignore the intermolecular forces that are present between the bromine molecule. The third is V, so volume of gas negligible relative to volume of container. So let's say the volume of gas is what, around 1 meter cube, and the volume of the container is 100 meter cube. That's a lot, but just as an example, please accept this. So even though the gas is 1 meter cube, how did this turn into a triangle? I do not understand. So since the even though the volume of the gas is 1 meter cube, it occupies the container that it is filled, like that it fills, right? And therefore we assume that the volume of this gas is negligible in comparison to the volume of the container which it occupies. That is basically what the third statement is. The fourth one is E, which means elastic collisions. For those of you who have done physics, this must be a very familiar term. Elastic collisions basically means that there is no loss of velocity, momentum, or kinetic energy in between the collisions. And the fifth statement is regarding time. So time of collision is negligible in comparison to time between collisions. So what it basically means is that when two atoms collide, okay, the time like that this collision happens for is negligible in comparison to the time between the collision. So when they will collide again. So let's say the molecules are here, right? Sorry, the atoms are here. They collide, and let's say this t is 0.001 seconds, okay? And for them to collide again, you would see them collide again after approximately 2 seconds. And therefore this time is negligible in comparison to this. That's basically what the fifth statement means. Now, you don't really have to go into an understanding of what each of these statements mean. You just have to by heart these statements and be able to recall them and use them whenever asked for. I hope that makes sense. The best way to remember it is Ravd. Okay. Now let's do a small question. I'll give you the values and you just have to do the calculations after pausing the video. So the question is, find the volume of carbon dioxide at temperature of 298 kelvins and pressure of 100 kilopascals. And the mass of carbon dioxide given is 2.2 grams. Pause the video and have an attempt yourself. Anyway, the way I do this in steps is first convert everything to the units required. So you see that the pressure given is in kilopascals, but you have to convert it to pascals itself. So kilopascals to pascals is 100 times 1000, which is 100 times 1000, which is 100 into 10 to the power 3 pascals. And this is the pressure, okay? And they've given you the mass of carbon dioxide, but in the equation PV is equal to nRT, you need the moles. How would you get the moles? And the moles would be M by MR. I understand that I haven't taught stoichiometry yet for the AS level, but this is something that you did in IGCSE and therefore should remember from your IGCSE years. So M by MR, so it should be 2.2 divided by the MR of this. So it'll be 12 into 1 plus 2 into 16. So that would be 2.2 divided by 12 plus 2 into 16. That would be 0.05 moles, right? So how would you find the volume of carbon dioxide? So the volume would be nRT by P. So the N is 0.05, R is a constant, 8.31, and T is given to 98 kelvins divided by the pressure, 100 into 10 to the power 3. And the volume you would get is, let me just do the calculation on a calculator. 8.31 into 298 divided by 110 to the power 3. So the volume you would get is 1.24 into 10 to the power minus 3 meter cube, right? And if you want to convert this to, let's say, dm cube, how would you convert it? To convert it to dm cube, you just have to multiply this value into 1000. And to convert it into meters cube, centimeter cube, you just have to do it into 100 cube. I hope you understood. Now let's take an example from a past paper that is a very recent paper as well. I believe it's February, March 21. So as you can see, the questions are very similar to what I've taught. So the first question in part B is that the Boltzmann distribution, which is something you're going to learn in the rates part, but we don't need that. We don't need that knowledge right now. Assumes that particles behave as an ideal gas, right? So state two assumptions of the kinetic theory applied to an ideal gas. So from these five, any two. So the easiest ones are E, so elastic collisions, and another would be attractive forces. Attractive forces such as IMFs between gas molecules are negligible. And that's easy 2 marks for just remembering this thing. Okay, now 2 grams of krypton gas, which is placed in a sealed container of 5 dm cube. So that's the mass and that is the temperature, right? Calculate the pressure in pascals of krypton in the container. Assume that krypton behaves as an ideal gas. So because it behaves as an ideal gas, you will have to use the equation PV is equal to nRT. The value of R is given in your data booklet, so you don't have to worry much about remembering it. So let's first convert everything into the units required. So V has to be in meters cube. So to convert dm cube into meter cube, 5 into 1000 is 5 into 10 to the power 3 meter cube. No, sorry, dm cube to meter cube, right? So I made a mistake, sorry. So to convert dm cube to meter cube, it has to be 5 divided by 1000 is equal to 5 into 10 to the power minus 3 meter cube, right? To convert temperature into kelvins, it has to be in thermodynamic temperature. You have to add by 273.15, so 120 plus 273.15, that's 393.15. Now you have temperature, you have volume, you have R, you need N. How would you get N? This is the same way as we did in the previous example question. N is equal to M by MR. And this is krypton, so it's a monoatomic gas. So the AR of krypton is something that you can get directly from your data booklet. So that is 2 divided by 83.8 if I recall correctly. So 2 divided by 83.8 which is 0.0239 moles. In the calculator, I got a much larger value, and when you're doing calculations, do not round until you get the final answer. So I'm just going to use the whole value in my calculator, but in my workings, I'll show that I'm using a rounded value. Anyway, so you have to make P the subject of the equation and RT by V, and therefore it would be 0.0239 into 8.31 into 393.15, the whole thing divided by the volume that we got, 500 to the power minus 3. So which would give me 8.31 into 393.15 divided by 5 to the power minus 3. Which would give me 15595 pascals. Now you take a look at the values given. You see that there's 3 significant figures here, 3 significant, 3 significant. Well, you can't really tell the significant figures of this, so because majority of the values are given in 3 significant figures, you have to round this to 3SF. So 15600 pascals. 3SF. Now yes, you got the right answer, but you always have to give it in the answer space provided, otherwise they will not give you the last mark. So that is easy, 5 marks in paper 2. Yeah, that is it for ideal gases. Now some miscellaneous facts that you need to know about the ideal gases. So these are some important miscellaneous. These I've gotten from solving doubts in past papers. Now, the gas that behaves most like an ideal gas is helium, and that's because it's monoatomic and it has almost negligible intermolecular forces because it does not have any other forces than van der Waals and it only has 2 electrons. So the strength of van der Waals attraction is very weak. Okay. Now another Okay, sorry about that. Anyway, another important fact is HCl, and it deviates to ideal gas behavior. To ideal gas behavior, NH3 does not show ideal gas behavior. And the reason why that is because NH3 has, as you can see, H, H, and H, has one pair of electrons, and because N is a highly electronegative molecule, it has partial charges, and hydrogen bonds can form between the NH3 molecules, and that's why the intermolecular forces are not negligible. So it does not behave like an ideal gas, and ideal gas equation, IgE, is followed at low pressure and high temperature, and this is based off of Boyle's law, where pressure is inversely proportional to volume. So the lower the pressure, the higher the volume, and therefore the particles are not as closely packed, so intermolecular forces are more negligible. And at higher pressures, volume is directly proportional to temperature, and that's why at higher temperatures the volume is directly proportional to the volume, and that's why intermolecular forces are more negligible. I hope that makes sense. And something else that's also more important is that a gas behaves ideally if PV by RT, which is basically N, is constant. Okay. By this being constant, I mean when these values are changed, except for RR can never change it to constant. When these values are changed, the N remains constant. So when those conditions are followed, the gas behaves ideally. Well, that is it for the states of matter and ideal gases lesson. If you do have any doubts, please leave them in the comment section.